Here we have the following problem. Given two spaces x and y, first of all we always write the maps from x to y, the class of up to homotopy of the maps from x to y in these brackets. So this denotes the set of homotopy maps from x to y. Now in case y it's I, which is the interval 0, 1, the first part tells you to prove that the set of homotopy maps from x to 0, 1 it's has a single element. So the proof goes like this. I is the interval 0, 1, so it's contractible. So we have a homotopy that contracts the interval to 0 or to any point you have in the interval, but this homotopy in particular contracts the interval to 0. Now pick any function f in this set. F defined on x with values in I, continuous. Then let's construct a homotopy using the homotopy h and the function f. So construct the homotopy g from x times I with values in I. G equals h applied to f of x and t. So notice that this is a well-defined homotopy. The image of f is in I and the h is defined on I times I. So this is a well-defined homotopy. Now if you apply for the point x0, then you will have h of f of x 0, and then you will use this line. So this means that you will get f of x. If you apply to f of to x1, then you using this line you will see that the result is 0. So in the end it implies that your map f it's homotopy equivalent with a constant map 0 on defined on x with values in I. Okay. The second part tells you to look to the same set of homotopy maps from x to y, but now x is contractible, the domain is contractible, and the codomain is path connected. You have to prove the same conclusion, that the homotopy maps between a contractible to a path connected space has a single element. So first we write the definition. So what x is contractible, then we have a homotopy between the identity of x and the constant map at x0, where x0 is a point in x. So x0 belongs to x. So then we can write the homotopy. So the homotopy is defined on x times I with values in x, a continuous map that on the points x0 gives you x, and on the points x1 gives you the constant x0. So now pick an element, a continuous map in the set xy, and pick an element z0 in y. So we would like to construct a homotopy out of the homotopy that we have h and the function f. So the function is defined from x to y, so then if you compose this function with the homotopy, we can create a new continuous map. g1 xt equals f applied to h xt. So it is well defined. It's defined from x times I with values in y. g1 of x0 is f of h x0, so it's f of x, and g1 of x1 is f of x0. So in conclusion, we have that the map f it's homotopy equivalent with the constant map f of x0. Now, the constant map f of x0 gives you an element f of x0 in y. So the next step of the proof will prove that all the constant maps are homotopy equivalent, and this is a result of the fact that y is path connected. So the proof will use the path connectivity of y. So let gamma be a path from f of x0 to z0, our arbitrary point z0 that we picked in y. This path actually defines a homotopy between the constant map f of x0 and z0, and the homotopy is defined by g2 of st equals gamma t. So this defines an homotopy between the constant map f of x0 and constant map z0. But constant map of f of x0 was homotopic with our initial map f. So in conclusion, we conclude that any map f we pick, we will have it homotopic with the constant map z0. And this will give you only one element in the set xy.